Hello everyone, welcome back to the Tensorflow tutorial this time, and today we're going to talk about the classification problem. Previously we already went through the regression problem, which is to predict a continuous value, but this time we're going to distinguish several different types. For example, the digital number from 0 to 9. In TensorFlow, it gave us a very good example, this one. All the digital numbers from handwriting number 1405 like this. So we're going to use this database and to train our neural network to predict those numbers. This example is called minced, and we can access the data by just use these two lines to download it and to process it. So for today's example, in here, again, you don't need to worry about the code in here. I will upload it into my GitHub, so you just find the link in my description, so you can just feel free to download it and practice by yourself. So we have the add layer function that's same as before, and we're going to define the placeholder as output layer and to calculate the error. And this time the calculation method is different from previous method, and this time we're going to use the cross entropy to calculate the error. And to train the error, initialize all variables, and then to train its every steps. And for 50 steps, we're going to predict predicting accuracy, to calculate the accuracy for our neural network. So let's look at the data first. For individual pictures or for individual digitals, it has 28 times 28 height and length, the length and width of this picture. So it's the one over here, the black color, are represented by some colors and some numbers in here, and the white color are represented by all zeros. The number is 0 over here. So this is what the computer can see from the picture. It's all a bunch of numbers, and this is for one digital pictures. So in this example, we have like 55,000 numbers or samples in this training sample, and for each of the pictures, it has 28 times 28 equals to the 784 pixels. So all these pixels are the inputs which we're going to input to my neural network, and then pass this 784 numbers to my hidden layer or output layer to finally get our outputs. And the output is not what you imagine. The output is an array, 10 possible positions array, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If the picture shows 1, then this array, we should put 1 in here, because the first one represents the digital number 0, and the first one represents the digital number 1, and third is representing the digital number 2. So in this example, they put 1 in the 1, 2, 3, 4, the fourth position, which means this one is the digital number 3, and they put another location as 0, because once you want to represent one class, just put the 1 in that location to represent that class. So in here, this is all samples, 55,000 samples, and 10 possible locations. Each black locations are the number 1, which means that this is 0, 1, 2, 3, 4, 5. So for this sample is to show the digital number 5, and for this one is to show the digital number 0. So this is the all possible position for this one, and for the digital number from 0 to 9. So let's start. So we know that we can download and just use these two simple lines over here. I just copy and paste, which is the one in here, right, in here, to download all these mixed digital numbers samples. And this is our database that we're going to use. And we're going to define what? Define the x as equals to tf.placeholders, tf.float32, and same as before, we put none over here to represent I accept all possible samples. So, and this one is the number of pixels in here. 28 times 28 equals to 784. So that is 28 times 28, 784, right? This is for our input, which is axis. And what is y-axis is similar to this one, but we have only 10 possible positions for 10 classes. 10 possible positions to put the digital 1 in whatever you want to represent the digital pictures. So this is the output. We have 10 positions. And to add, in this example, we just only add one layer, which is the output layer. So this one we can directly output the prediction equals to add layer, which is the function over here we have defined before. If you don't know that, you just check it out in my previous example. And x-axis, the inputs, and the insides is all the pixels, the number of pixels. So that is same as this one, 784. Then the output is 10 because we output 10 locations for each of the classes. And the output is only the probability of that. We will talk about this later on. And the activation function we're going to use for today is called softmax. This one is to calculate the probability of each class. So in this output array, we will see in the prediction, it's not like 0, 0, 1, 0, 0, something like that. It will look like this one. For example, 0.3, 0.1, 0.1, 0.9 should be added together to 1. So we just choose the maximum number of this location to represent the class of that location. For example, in this location we have the maximum number, which is 0.9, and others are 0.0 something like that. So we choose this one because this one have the highest probability to represent this class, which is 0, 1, 2, 3, which is the digital 3. That is the meaning of the output prediction. So for example, the output could be 0.1, 0.1, 0.01, 0.6 or something else. And this one, if this one is the maximum number, then we just we can compare with looks like 0, 0, 0, 0, 1. It will be looks like this one in the real data. So if this one is the maximum number, so it looks like this one, and to represent 0, 1, 2, 3, then digital number 3. Okay, let's continue. If you have any issues to understand this, just let me know and leave your comments below. And we're going to calculate the error between prediction and real data, and for today, the calculation for the error is a different way. Typically we call these methods is cross entropy. That is TF dot reduce mean and minus TF dot reduce sum, and ys times TF dot log. It's a pretty long prediction, then reduction in this 1. So if you don't know what is this, you just can imagine or think about this as the loss. So we calculate the loss between the real data and the prediction over here. But the calculation method is a different method to use. And we're going to train step, same as before. We're going to use the gradient descent, train gradient descent optimizer. The learning rate we choose is 0.5, but you can choose whatever you want, but less than 1. Minimize this cross entropy, which is the loss. Good. So session run initial all variables, then we could use, for this time we separate the training data and the task data. If you can read this one, input the total data set is the minced data set, but in training we're going to use the training data, which is minced train. This is the training data. We're going to have 55,000 training data, and how many we get for the task data? Let me check it out. For task data, I don't know how many task data we have, but should be less than training data. Anyway, just keep going. Next batch. What this means is to only choose 100 samples from this 55,000 samples. Only choose 100 each time from this 55,000 data, and to do so, we're going to become the gradient descent going to become the stochastic gradient descent. If you don't know stochastic gradient descent, just Google it or look at the Wikipedia, so that you will know, you will have the better understanding in this one. But in my tutorial, it takes so many times to explain that, so this is out of scope of my tutorial, so you just check it out by yourself. Run. Basically, to use the stochastic gradient descent, is similar to this way over here. It is better compared with the pure gradient descent to use the whole bunch of data, that is 55,000 of data, train this neural network each time, because this one to train all bunch of data is computationally expensive in this training process. But if you only train 100 of them, it will be relatively cheaper for computation. So we choose to use the stochastic gradient descent instead of the pure gradient descent. So train step and feed dictionary, which we're going to have access is batch access, and ys is batch ys. Oh, good. And this is for every training step, and for each 50 steps, we're going to print. Let's just finish this and compute the accuracy for our task data. Means test image and means test labels. This is the task data. If you see, this is different from the training data. The reason for separating the task data and the training data is that if you mix this together, if you use the same group of data to train and also use the same group data to task, it will cause a lot of error. It's called extra error in this training process. But if you separate two groups of data, use this group of data to train and use this group of data to task, or these two groups of data becomes to independently to be trained and to be tested. So this is by doing this, it will be better to compare with only use one group of data. So the x-axis will be image, which is the axis, and the task data for labels, which is the y-axis, and we're going to define this compute accuracy function in here. So I'm going to define this compute accuracy, and we're going to have the validation x-axis and validation y-axis, and I just copy those commands in here. So basically, it's going to compare use the validation x-axis, which is the task data, to predict for the y prediction, and compare the prediction with this task data y-axis to calculate the correct prediction, which is how many predictions are same as the real data. For initial stage, for example, if we have 10% of the training task data, the results are the same as the real data, that's the accuracy will be 20%. Maybe later on, the accuracy will becomes to 50%. That 50% means that 50% of the task data will successfully predict the right value in the reality. For example, it's the right value for the validation y-axis. So I think that is all for that. Just try it out. So firstly, you're going to, if you don't have this means the data, you're going to download it. It takes some time to download it. So for this one, I've already downloaded this data set. So it's just extracting the means the data, and then to print the accuracy result for every 50 steps. So as you can see, the 0.0974, which means there is only 9% of the predicted value is same as the real value, and later on it changed to 62% and 80% or 86% of the accuracy, and at the end of training it takes to 87% of the accuracy. Later on, this correct answer will be improved or increased, so more prediction will look like the real data. So that means the machine learning or neural network is learning something. So this is all for today. You can try it out for your example. For the next tutorial, we're going to talk about the overfitting problem and to use the dropout method to deal with the overfitting problem. Hope you will like this video, and if you want to watch more about the TensorFlow or machine learning, you can actually subscribe to my channel, and see you next time. Thank you, bye.